Check 1 2. Testing 1 2. Check 1 2.
Can you dig any deeper now? I gave you all I own, put you on this golden throne, but I'm a little stronger now. You cashed in on my promises, you know I'm too generous. Now I've learned to never help you out, 'cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now, a little stronger now. You know I'm too generous. Now I've learned to never help you out, 'cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now, a little stronger now.
give a little bit.
At Amazon, we've got millions of toys and games to choose from this holiday for kids of all ages, with free shipping on over 100 million items. So visit Amazon and give a little love this holiday.
It's like I'm living in a daydream. Got your love all over me. I can feel something starting. Take me all the ways you want me. 'Cause too many times I complicated this love. Too many times I don't know when to shut up. But every time you keep pulling me closer, you don't let me down. You got the feeling, I know. You got the feeling, I know you're there. You got the feeling, I know. You got the feeling, I know you're there. You got the feeling. You
welcome, and I would like to thank you for holding and inform you that your lines are on a listen only during today's conference until the question and answer session. At that time, if you would like to ask a question, you will press star then 1. Today's call is being recorded. If we have any objection, you may disconnect. Now I'd like to turn to Felicia Chow. You may begin.
Thanks, Ed. Hi, I'm Felicia Chow, Public Affairs Officer at NASA headquarters in Washington, D.C. Welcome to today's media teleconference to discuss new discoveries from NASA's Kepler spacecraft. We have 4 panelists joining us today. For those watching via Ustream at nasa.gov/live, please note that there will be a 30-second delay in the streaming to the actual telecon. For all the graphics the panelists will be using, please go to www.nasa.gov/Kepler. Each panelist will give a short briefing, then we'll move to the question and answer session, accepting questions from media that dialed into the phone bridge and those that submitted questions via Twitter using the hashtag AskNASA. We will also be answering questions at 3 p.m. Eastern today through a Reddit AMA or Ask Me Anything. For more information, please go to the science subreddit, www.reddit.com/r/science for more information. The full link to the Reddit AMA is also on our press release. This media telecon will be limited to 1 hour. Today's panelists are Paul Hertz, Astrophysics Division Director at NASA headquarters in Washington; Chris Chalou, Machine Learning Researcher at Google Artificial Intelligence in Mountain View, California; Andrew Vanderberg, NASA Sagan Fellow and astronomer at the University of Texas at Austin; and Jesse Dotson, Kepler's mission scientist at NASA's Ames Research Center in California's Silicon Valley. And with that, let's get started. Paul?
Thanks, Felicia. Today, we're glad to be announcing a discovery made by scientists analyzing data from NASA's Kepler Space Telescope. By applying an advanced type of machine learning called a neural network to the Kepler data, these scientists have found, for the first time, an 8th planet in a distant planetary system. This discovery of an 8th planet in the Kepler 90 system ties Kepler 90 with our own solar system for having the most known planets. Kepler has already shown us that most stars have planets. Today, Kepler confirms that stars can have large families of planets just like our solar system. Kepler was the first telescope on the ground or in space capable of detecting Earth-sized planets orbiting Sun-like stars. Figure 1 shows NASA's series of missions, both currently flying and being developed for launch, that will advance the search for habitable exoplanets and the search for life beyond Earth. The TESS mission will be launching next year in 2018, and the James Webb Space Telescope will be launching the year after that in 2019. When we launched Kepler in 2009, we didn't know if planets around other stars were common or rare. Because of Kepler, we now know that almost every star in the night sky has a family of exoplanets orbiting it. The Kepler Space Telescope spent 4 years staring at more than 150,000 stars 24/7, 365. It looked for the small reductions in the star's brightness caused when one of that star's planets passed in front of it. As shown in Figure 2, this causes a characteristic U-shaped dip in the star's light curve. A light curve is a graphic showing the time change in the brightness of the star. Kepler completed its 4-year mission in 2013, and since then it's been observing different parts of the sky. The archived Kepler data is a treasure trove of scientific discoveries waiting to be revealed. Today's announcement is one such discovery. Today's announcement shows what happens when new scientific methods are applied to archival scientific data. This discovery was made by Christopher Chalou, a machine learning expert at Google AI, and by Andrew Vandenberg, a NASA Sagan Fellow in the Astronomy Department at the University of Texas, Austin. Now I'm going to turn it over to Christopher to explain how machine learning was used to find planet Kepler 90I.
Thank you, Paul. Hi, everyone. I'm Christopher Shalou. I'm a senior research software engineer at Google AI, and I'm excited to explain how we discovered 2 new planets in data collected by the Kepler Space Telescope. The planet we're focusing on today is called Kepler 90I and is the 8th planet discovered around the Kepler 90 star. This makes Kepler 90 the first star known to host as many planets as our own solar system. What's different about this discovery is that we used machine learning to help identify planets that were missed by previous searches of the Kepler data. Machine learning is a way to teach computers to recognize patterns. It's one approach to artificial intelligence, which means it's a way to make computers perform intelligent tasks. The key idea is to let the computer learn by example, instead of humans programming specific rules. For example, we would teach a machine learning system to recognize images of cats and dogs by showing it thousands of labeled images and letting it learn for itself which patterns look like cats and which patterns look like dogs. Our idea was to turn this technique to the skies and teach a machine learning system how to identify planets around faraway stars. At Google, my research is focused on a particular type of machine learning called a neural network. Figure 3 shows a diagram of a neural network that identifies images of cats and dogs. A neural network is loosely inspired by the structure of the human brain. It's made up of layers of neurons that each do a simple computation and then pass information on to the next layer of neurons. You can think of the neurons as switches that activate depending on the patterns of neurons that were activated in the previous layer. With many layers of connected neurons, the neural network can learn to recognize complex patterns, such as cats and dogs. Neural networks have been around for decades, but in recent years they've become tremendously successful in a wide variety of problems. For example, neural networks can translate between languages, recognize human speech, identify objects in images, and even detect breast cancer tumors. And now we've shown that neural networks can also identify planets in data collected by the Kepler Space Telescope. In fact, the neural network that we used to discover these 2 planets is very similar to the kind of neural network that we would use to classify images of cats and dogs. As technology advances and we continue to collect more and more data in astronomy and other scientific fields, machine learning will become increasingly important for keeping pace with all this data and will help us make more discoveries than ever before. I became interested in applying neural networks to astronomy when I learned that the Kepler mission had collected so much data that it was impossible for scientists to examine it all manually. Instead, scientists selected the strongest signals, which are the most likely to be actual planets, to receive the most attention. The strongest signals were examined with human eyes and automated tests to identify which signals were caused by actual planets. This process is like looking for needles in a haystack. Over 30,000 signals from the Kepler Space Telescope were examined, and about 2,500 were confirmed to be actual planets. Now, if we wanted to search for planets in the weaker signals from the Kepler Space Telescope, it would be like looking for needles in a much, much larger haystack. There are simply too many weak signals to examine using the existing methods. But machine learning really shines in situations where there is too much data for humans to examine for themselves. Andrew and I developed a neural network that can identify planets, even if the signal is very weak. To train our neural network, we used a set of 15,000 Kepler signals that had already been examined and labeled by human scientists. After showing our model these 15,000 signals, it learned how to distinguish patterns that are caused by actual planets from patterns that are caused by other objects. When we tested our model on signals it had never seen before, it correctly identified which signals were planets and which signals were not planets 96% of the time. Figure 4 shows how we used our model to identify 2 new planets in a search of 670 stars. These 2 planets have weak signals that were missed in all previous searches of these stars. As you can see, The data points on these two signals are much more spread out than the strong U-shape we saw in Figure 2. But even though the two signals were very weak, our model was highly confident that these two signals were caused by actual planets. One of these two planets is called Kepler 80G and is the sixth planet in its system. But the planet we're focusing on today is called Kepler 90I and is the eighth planet in its system, which brings Kepler 90 into a tie with our own solar system as the star known to host the most planets. This is a really exciting discovery, and we consider it to be a successful proof of concept for using neural networks to identify planets, even in challenging situations where the signals are very weak. We have some new ideas for how to improve our neural network, and once we do, we plan to search all 150,000 stars in the Kepler dataset. We hope that using our technique, we'll be able to find lots of new planets, including planets similar to the Earth. And now I'll pass to Andrew to tell you a bit more about the newly discovered planet, Kepler 90I.
Thanks, Chris. Hi, everyone. My name is Andrew Vanderberg, and I am a NASA Sagan postdoctoral fellow at the University of Texas at Austin. I study small exoplanets, mostly using data from Kepler, and I'm extremely excited to be here talking to you today about this cool discovery. I'm now going to tell you a little bit about the new planet, Kepler 90I, and what we know about it and the other planets in its system. First, I'd like to draw your attention to Figure 5, which shows the Kepler 90 planets in order on top, and our solar system planets on bottom. Here, the sizes of the planets are to scale, but the distances between the planets are not. The new planet's host star, Kepler 90, is a G0 type star that is a little bit hotter, larger, and more massive than the Sun, and which lies about 2,500 light-years away in the northern sky. Before this work, we already knew that Kepler 90 hosted 7 planets. We knew of 2 planets a bit larger than the Earth, orbiting close to their star, 3 planets a bit smaller than Neptune, orbiting further out, and 2 outer planets about the size of Saturn and Jupiter. The new planet we found, Kepler 90I, is the smallest of the bunch, and orbits just outside the inner 2 planets. The new planet is small enough that we think it is probably rocky and doesn't have a thick atmosphere like the gas giant planets farther out in the Kepler 90 system. Kepler 90I is not a place I'd like to go visit, though. The surface is likely scorching hot. We calculated that it probably has an average temperature of about 800 degrees Fahrenheit. Still looking at Figure 5, I want to point out that like our solar system, the planets around Kepler 90 seem to follow a pattern, and that the smaller planets are found close to their star, and the bigger planets are found further away. In our own solar system, this pattern is often seen as evidence that the outer planets formed in a cooler part of the solar system, where water ice can stay solid and clump together to make bigger and bigger planets. The pattern we see around Kepler 90 could be evidence of that same process happening in this other system as well. Now I'd like to direct your attention to Figure 6, which shows the orbits of the Kepler 90 planets to scale on the left, alongside the orbits of the solar system planets on the right. The inner 2 small planets, Kepler 90b and c, orbit their star every 7 and 9 days. Just outside, the new planet, Kepler 90I, orbits the star every 14 days. The 3 sub-Neptune-sized planets, Kepler 90d, e, and f, orbit their star every 60, 92, and 125 days. And the 2 gas giant planets, Kepler 90g and h, orbit every 211 days and every 332 days. As you can see in Figure 6, an interesting fact about the Kepler 90 system is that all the planets are found scrunched very close to their star. All 8 of the planets around Kepler 90 orbit closer to their hosts than Earth orbits the Sun. This could hint that the 8 planets around Kepler 90 may have formed more spread out like the planets in our own solar system, and then somehow migrated to the orbits we see them in today. The next slide, Figure 7, is just a zoomed out version of the image we were just looking at. Again, I'm showing the Kepler 90 system to scale on the left, alongside the solar system planets on the right. The solar system has 4 planets relatively close to the Sun, and 4 farther out, while Kepler 90 has all 8 planets close in. That may not be the whole story, though. It's very possible that Kepler 90 has even more planets that we just wouldn't know about. On the left-hand side of the graphic, I've highlighted orange and blue regions in the Kepler 90 system. Kepler has searched for planets around Kepler 90 only in the small orange highlighted region in the center. The large blue highlighted region is largely unexplored, If planets in that area do exist, they probably would not have transited enough times while Kepler was watching for us to know that they were there. There's a lot of unexplored real estate in the Kepler 90 system, and it would almost be surprising to me if there weren't any more planets around this star. In Figure 8, I'm showing the number of all known confirmed planetary systems with 1 planet, 2 planets, 3 planets, etc. Each dot represents one known planetary system. We know of many single planet systems, shown at the bottom of this diagram, and progressively fewer systems as we increase the number of planets, all the way up to Kepler 90 at the top of the diagram, the only known 8-planet system outside of our own. Kepler 90 is the first exoplanet system with 8 planets, but almost certainly will not be the last. I suspect that many of these other systems have more undiscovered planets which we just haven't seen yet. When I think about this, I start to wonder, is an 8-planet system like our own solar system really that extraordinary? For the first time since our solar system planets were discovered thousands of years ago, we know for sure that the solar system is not the sole record holder for the most planets, and we've just scratched the surface. Maybe there are systems out there with so many planets that they make our 8-planet solar system seem ordinary. And now I'll pass to Jesse, who will tell us about Kepler's impact on our knowledge of exoplanets and where we might go from here.
Thank you, Andrew. I'm Jessie Dotson, the project scientist for NASA's Kepler mission. We've come a long way in our understanding of planetary systems since the Kepler Space Telescope was launched 8.5 years ago. As shown in Figure 9, at that time we knew of 326 exoplanets, most of which were similar in size of Jupiter and all of which were much, much larger than our Earth. Today, as shown in Figure 10, we know of over 3,500 confirmed exoplanets, and just over 2,500 of those were found in data from the Kepler Space Telescope. These planets range in size from larger than Jupiter to smaller than Earth. In just a couple decades, thanks largely to Kepler, we have gone from suspecting exoplanets existed to knowing that there are more exoplanets than stars in our galaxy. These kinds of leaps in knowledge usually involve new types of observations and new ways of interpreting those observations. The Kepler-driven revolution in our understanding of how common exoplanets are has been facilitated both by unprecedented observations performed by the Kepler Space Telescope and by significant improvements in our ability to interpret the resulting data. The results we're discussing today demonstrate that while data collection of the original Kepler field ended in 2013, advances in algorithms to process and interpret that data are continuing to yield progress in our understanding of planetary systems around other stars. The discovery of an 8th planet in the Kepler 90 system is a result of an exciting but early-stage research to apply neural network to that data set. Before Chris and Andrew's work, Kepler 90 was tied with the TRAPPIST-1 system with 7 planets each. The Kepler 90 system now ties our own solar system for the most number of known planets. While our solar system and these 2 other planetary systems each have 7 to 8 planets, differences in the host stars, sizes of planets, and length of the planets' years clearly demonstrate the diversity of planetary systems. And I am so excited to see where this goes next. As the application of neural networks to the Kepler dataset matures, who knows what potential insights might be gained? In addition, NASA continues to use the Kepler Space Telescope to observe additional regions of the sky within the plane of the solar system. To date, we've observed an additional 200,000 stars in 1,000 square degrees along the ecliptic plane. I'm on the edge of my seat to see what Chris and Andrew might learn when they turn their algorithms to those regions of the sky also. And looking even further into the future, combining sophisticated algorithms like those Chris and Andrew have developed with the future missions NASA has planned is sure to yield exciting results which will continue to illuminate the nature of planetary systems and how those other systems compare to our own.
Thanks, Jessie. And with that, we'll start the question and answer session. We've got reporters on the telephone bridge today. We'll need to limit everyone to 1 question and 1 follow-up. Once everyone has had a chance to ask a question, and if time permits, we'll start from the beginning again. Our operator should identify you, but if not, please identify yourself, your media affiliation, and then direct your question to a specific panelist if possible. For those dialing in, please push the *1 keys on your telephone to be placed in the queue. To use Twitter, please send your questions to the hashtag AskNASA. And with that, let's go ahead with Marcia Dunn.
Yes, can you hear me?
Yes, I can.
For Dr. Hertz, probably, what do you think the odds would be of Kepler ever having discovered this eighth planet? Do you think it would have taken years more, if at all? And for Mr. Vandenberg or Mr. Shalui, you said that you wanted to study all the stars identified by Kepler to date. How long of a process will that take you as opposed to the old-fashioned way?
So, Marcia, I'm going to let Chris answer both parts of that question because I'm sure that he has an assessment of whether this planet could have been found without the AI techniques.
Hi there, this is Chris. Yes, it was possible to see this planet once we had identified the planet with the machine learning model. The key part of this is that the machine learning model was simply able to look at more signals than it would be reasonably possible to expect humans to look at. So yes, if humans were to have looked at a much larger set of signals, it would have been possible to find this planet using the previous techniques. But as I mentioned, humans had already examined 30,000 strong signals, and so if they had turned to the even weaker signals, they would have had to search a much larger number of signals in order to find this Kepler 90I planet. So the key contribution of machine learning here was that it was able to search a much larger number of signals than humans would have been able to do in a reasonable amount of time. And would you be able to repeat the second part of that question, please?
Yes, I think you mentioned that there are, 150,000 stars identified by Kepler as potential solar systems. How long does your machine take to go through all those versus the old-fashioned way?
Yeah, okay. So I don't remember the exact numbers off the top of my head, but I believe we were taking about 5 to 6 hours to search each of the stars in the 670 stars that we searched in this project. So actually, that process is where we run some computer software that's not a machine learning model, and we ask it to detect signals on the star. And so this is the same technique that was previously used, and previously that software was only outputting the strongest signals for humans to examine by eye. And so what we're doing when we run this software is we're asking it to output the weaker signals. And so in our early tests on 670 stars, it's been taking us about 5 to 6 hours per star to run that initial algorithm to actually detect the candidates. But once we have the candidates, it's actually very fast comparatively to actually run the machine learning model and ask it which of those candidates are the most likely to be planets.
And lastly, is this latest discovery, is it a candidate or is it confirmed? How are you characterizing it?
I think I'll let Andrew take this one.
Hi, this is Andrew. We have statistically validated this candidate. After we identified it with our machine learning methods, we went in and very carefully examined the data, made sure that there were no false positive scenarios that were credible. And we used previous methods, including what has been used for large Kepler releases in the past, called validation by multiplicity and statistical validation, to very carefully check that this is almost certainly a real exoplanet, about 1 in 10,000 false positive probability.
Thank you.
Next we have Business Insider, Dave Mosher.
Hi, thank you for taking my question. I wanted to spring off of Marsha's question about the confirmed versus candidates. I mean, you mentioned there was another planet too. What total are we at now for Kepler in terms of the number of planets it's found? And then I have sort of a more interesting question to follow that, and perhaps this is one for Chris, but this is a form of automation. I guess I would ask, will this put any astronomers out of work or maybe have the the inverse effect?
Hey, this is Jessie. I'd like to jump in here just for a second. So for Kepler, we are at 2,525 confirmed planets that have been observed by the Kepler spacecraft. That's both in the original Kepler field as well as in the subsequent fields we've been doing along the ecliptic. So that's a pretty good haul. What was the second part of your question?
The second part of my question was I think for Chris, or perhaps anyone who wants to answer, but this is another form of automation, and we're seeing more of these processes pop up. I guess I'm asking, will this put any astronomers out of work, or will this sort of work alongside them? Perhaps.
I can answer that one. I can answer that one also. So this will absolutely work alongside astronomers. To some extent, in a very real sense, the work that we did at NASA to learn how to vet these signals and identify what is likely to be a planet and what is likely to be a false positive, Chris and Andrew trained their machine learning based on the classifications that human astronomers made. And so you're never going to take that piece out. You've got to have those initial classifications in order to train your machine learning, and then it can go through a lot more signals than humans can. Did I get that right, Chris?
Yes, this is Chris. Thanks for the question. I agree with what Jessie said. Also, the way I see it is what we've developed here is a tool to help astronomers have more impact. Hopefully this is a way to actually increase the productivity of astronomers. It certainly will not replace them at all. In fact, I hope that this may perhaps give people more reason to go into astronomy in order to use sort of advanced technologies like this in the future.
Okay, thank you. Next we have Mike Wall from Space.com.
Thank you, guys. Got a couple for Andrew, probably. Could you just talk a little bit about what, like the other planet, Kepler 80G, is probably like? I mean, I saw you guys said it's probably Earth-sized or thereabouts. And then another quick one. This whole Kepler 90 system, it's so strange that everything's so squished so kind of close to that star. Could you talk about how stable that might be, or what might happen to that system over the long haul? Thank you.
Sure. So the first question was about the other planet, which we discovered and validated, called Kepler 80G. And I actually really like this planet. It's got a lot of really cool characteristics. So this is a planet in about the same orbital period as Kepler 90I. It has an orbital period of about 14 and a half days. And it's in a 5-planet. It was in a previously known 5-planet system. So this is the 6th planet around that star. The star is a redder star. It is closer to a M-type star, maybe a K dwarf, late K dwarf, early M dwarf. And it has an interesting characteristic that 5 out of the 6 known planets, including this new planet, appear to be locked together in what's called a resonant chain. This means that the mutual gravitational interactions between these planets keep their orbits very precisely aligned with one another, for lack of a better word. So the interesting thing about this is that we actually could have predicted what the orbital period for this new planet is before we found it, based on some mathematical relations that were first worked out by Laplace centuries ago. And if we used those predictions, we would have predicted the orbital period to within about 2 minutes of what we actually measured. So that's like meeting someone and predicting what their sibling's height is to about the precision of the width of a human hair. And I believe your second question was about what whether this Kepler-90 system is dynamically stable. It is weird that Kepler-90 is one of the squished compact systems, but it's actually not that uncommon. In Kepler data, we see this quite a bit. There are many systems that are much more tightly packed than our own solar system, and they do appear to be dynamically stable. So it probably will last for quite the long haul.
Great, thank you.
Okay, so before we go back to the phone lines for more questions, we're going to answer some questions via social media. So we've got a question here from Hikigami Slayer. What other areas of space exploration do you think machine learning can be applied to? I think this would go to Chris and maybe Andrew.
I can start talking a little bit about this one. Chris and I have brainstormed other ways that we might use machine learning in astronomy, but the real answer is that I think machine learning can be used in a lot of different ways to replace tasks that people have to do kind of tediously and repetitively with a computer. So, for example, you can imagine that other types of missions, for example, microlensing planet searches, could use machine learning to identify planets in those data sets as well. We've also thought about using machine learning to try to get better measurements of the radial velocity of stars, how quickly stars are moving towards or away from us, so we can better detect planets using the Doppler wobble method.
Okay, thanks. And kind of similar questions from Gary Bryant. What processing speeds are the computers that run the AI technique, and how long did it take for this algorithm to comb through the existing data?
Yes, this is Chris. I'll take this question. So actually, I mentioned that the training set, which is the number of already labeled signals that we trained our neural network on, contained 15,000 examples that were already previously labeled by human scientists. But actually, at the scale of machine learning, this is actually a really small training set. Typically, we deal with models which have at least millions of training examples. So this was actually a pretty small and easy model to train. In fact, it only takes about 2 hours to train this model on a regular desktop computer. And I might also add to this that we built this model and trained this model using TensorFlow, which is an open source machine learning software library, and that was produced by Google, and we will actually be releasing all of the code needed to process the data and train this model in TensorFlow. We'll be releasing this soon, and then sort of anybody can come in, and without any specialized hardware or anything, we'll be able to train the exact same model that we trained, and potentially also run their own searches of the Kepler data if they so desire. And they should be able to do this without any specialized hardware.
And just to piggyback on that, this is Jessie from NASA Ames. All of the data from the Kepler mission is publicly available. Anybody who wants to can go to the NASA archives and download it and combine that with the tools that Chris is about to release.
Thank you. We're going to go back to the phone lines. Next we have Nicholas St. Fleur from the New York Times.
Hi there, yes, and thank you for taking my question. I have a fun one for you guys here. So as you're announcing, you found this 8th planet in the Kepler-90 system, and our solar system has 8 planets as well, so it's kind of like this intergalactic tie when it comes to planets here. But as you're aware, astronomers like Mike Brown are investigating whether there might be a 9th planet in our solar system. So does this set off kind of a race here, seeing which one has who could find the 9th planet first between Kepler-90 and our solar system? Thanks.
this is Jesse, and Andrew can pile on afterwards, but I actually think this is a fascinating topic. To me, this is like watching scientific discovery in action, right? So the ninth planet is a theory that explains some unusual orbits we're seeing in dwarf planets and small solar system bodies out in the outer solar system. So it's suspected that it might be there, but we have no definite proof. Similarly, as Andrew talked about, there's a huge part of the planetary system space around Kepler 90 that we haven't searched yet. And so it's kind of cool to see which one's going to be proven next.
Thank you. Next we have Robert Verger from Popular Science magazine.
Yeah. Yeah, hi. I'm wondering, now that we see, AI and neural networks making discoveries like this, does this spell the end of citizen science? Projects like Zootopia and Planet Hunters. Does this mean that, why use citizen scientists when you can train a neural network to do their job better and faster?
I can talk about this. So this is Andrew. I work quite a bit with citizen scientists, and they're absolutely fantastic. One of the things that they excel at is finding things that are weird or things that don't look like things that they've seen before. And as I understand it, neural networks struggle with that. If you show a neural network something that it's never seen before, it might not know what to do with it. Whereas citizen scientists can go through and they can identify unusual-looking transits. A couple months ago, we worked on a result where a citizen scientist identified transits which might be from comets in Kepler data, and he identified them as unusual because of their shape. They didn't look like normal transits. I'm not sure how a neural network would have been able to look at that and decide that this was something interesting. Chris can add on if you want as well.
Yes, this is Chris. I'd like to add on to that. That was yes, I agree with Andrew's points there, and it's also true that a neural network is good at identifying things it's seen before, and typically it needs to see them quite a few times before it can learn exactly what it's looking at. So, to Andrew's point, it's going to be difficult for a neural network to identify these other really interesting things that citizen scientists are coming up with. And also, to bring back to my previous point, I also hope that this may bring in some new citizen scientists with more of a background in machine learning, or will sort of encourage current citizen scientists to also try and use machine learning in their efforts as well.
Thank you so much.
Thank you. Before we go back to the phone lines, we're going to answer some questions off social media. So this is probably for Chris or Andrew. Can your algorithm detect anything deeper than the fact that it's an exoplanet? Can you also identify which planets may have life?
This is Chris. So actually, our current version of our model, we input a candidate signal, and what we get out is the probability that the model believes that this signal is a planet, an actual planet, as opposed to some other signal that could have occurred. So, for example, with the newly discovered planet Kepler 90I, when we fed the signal into our model, what it actually spat out was 94.2%, which means that it was highly confident that this model was a real planet. But that is the sole output of this model at the moment. Now, one thing we're kind of planning on doing in the near future is actually asking the model to output perhaps a more fine-grained categorization. So if the model the model should output the probability that it's a planet, but if it's not a planet, it should also output perhaps the probability that it's a binary star or a star spot or some sort of other type of false positive. So we have plans to add sort of that extra layer of output to the model in the future.
This is Andrew. I'd also like to jump in and just say it'll be, I don't think with Kepler data alone we can say anything about the presence of life on any planet. That will require future missions, in particular missions like the James Webb Space Telescope, which can go in and study these planets spectroscopically, and they can identify features in the atmospheres of these planets. Kepler is really just focused on seeing if planets are there. Searching for biosignatures will be something that has to be done with a more sophisticated instrument.
Okay, I'm going to do one more question from social media and then go back to the phone lines. The question is, we didn't talk much about ADG. Tell us more about it. What kind of planet is it?
This is Andrew. So I talked a little bit about Kepler ADG a few minutes ago, but I'll say a little bit more. As I said before, it's about the size of Earth. It's in a 14.6-day orbital period, I believe. And it's in a 6-planet system, 5 of which are in a resonant chain, which I described. The star is cooler than the Sun. It's probably a red dwarf, either a late K dwarf or an M dwarf. And all of the planets in this system orbit very, very tightly packed in. They have orbital periods all less than 14 days, and one of them is extremely short. It's about 0.8 days, I believe.
Thank you. Next we have Dan Cleary from Science Magazine on the phone.
Hi, thanks for all your answers on this. I just wanted to ask, in the Kepler 90 system, you have these, well-ordered orbits in nice progression of sizes. Is there any evidence as to whether, they formed in those positions from a particularly massive disk, or whether they migrated from further out and into that position?
This is Andrew. I can talk a little bit about that. So first of all, I'd like to say that we don't entirely understand the process of planet formation and the process of planet migration. Back before we detected exoplanets, we thought we did, because we saw one example, which was our solar system, and we came up with theories that described the solar system's formation extremely well. We can predict where the planets will form, what their masses will be roughly, and everything seemed to work great. And then we started finding exoplanet systems which totally turned all of those theories on their heads. We found giant planets very, very close to their host stars called hot Jupiters. We don't really understand how those form or come to be where they are. And we, in general, don't believe that we have a comprehensive understanding of how planets form and come to be in their current orbits. That all being said, if we kind of go back to the theories that we came up with based on our own solar system, we can make some speculation about the Kepler 90 system. I mentioned earlier that the Kepler 90 planets seem to have this order where the big planets are further out. And in the solar system, that is taken as indication that planets like Jupiter and Saturn formed beyond what is called the snow line, where water can exist and ice form and help planets clump together. All of the Kepler 90 planets, though, are inside the snow line. So if you believe that they formed this way, then there must have been some way for them to migrate into where we see, possibly through their protoplanetary disk. But I'll go back to my caveat at the beginning. I don't think we really know enough about how these planets form, especially given the huge dump of information that Kepler has given us in the last 9 years, to say for sure how we believe exoplanets in general form and migrate.
Okay, thanks.
Next we have Monica Young from Sky and Telescope.
Hi, this is Monica. Thanks for talking with us. I just was curious about what you had said earlier about the supervised learning. You said that you offered it training examples, and I was curious if you had any plans to ever make it unsupervised learning so that you don't offer it any labeled examples, which obviously take a lot of human input, and for further data sets that might not be possible. So I was just curious what your plans were for that.
Hi, yes, this is Chris. Thanks for your question. To clarify what you said, yes. So this where in this project we use a type of machine learning called supervised machine learning, which means we relied on a large set of data that had already been labeled. In other words, we already had the right answers, and we told our model what the correct answers were. There is another approach to machine learning called unsupervised learning, where you actually don't have the right answers. All you have is a large amount of data, and you turn a model to that data and ask it to learn things, even though you haven't specifically told it what the right answers are. This is an exciting type of machine learning as well. Obviously, it's great when you don't actually have a large labeled training set, and it's actually a very active area of machine learning research as well at the moment. I would say that most of the large successful applications of machine learning that you'll see actually have come about with supervised machine learning, and unsupervised machine learning is sort of not necessarily as clear cut how to apply it to a given problem. So I think it would be exciting to try and explore some unsupervised techniques on this data, but we don't have any specific plans at this time.
Okay, thanks. And if I can just ask a quick follow-up too, you mentioned that you had 96% accuracy for these planet detections. Can you just clarify if that was the false positives or false negatives, or what you were measuring there?
Yeah, so in this case, the 96% accuracy, we actually held out a small number of, it was actually 10% of the examples that had already been labeled by the human scientists, and we didn't show them to our model during training. And once it was finished training, we actually ran our model over those, over that 10% of signals it had never seen before to see how it did. And the accuracy number in this case is simply the number of correct classifications, where a classification here is the classification, is this a planet or is this not a planet, just divided by the total number of things that it predicted.
Great, thank you.
Next we have Irene Klotz from Aviation Week.
Hi, thanks very much. I have two quick questions. First is, are you all planning on publishing a paper about this? And the second question is, I think I heard the answer to this, but just to clarify, the difference between the technique you used to find the exoplanets this time, aside from hitting pay dirt, is that the software was modified to scan for weak signals, not strong ones. And is there any other difference between what changed in previous efforts to use neural networks to look for exoplanets? Thanks.
I can take a stab at that. So this is Andrew. Yes, we have published a paper. It's not published yet, but it has been accepted for publication. It'll be posted on the archive tonight, and a copy of the paper is available for download now. I believe it's in the press release, but maybe someone can confirm that for me.
Yes, the current link can be found in the press release.
Yeah. And the second question was asking about what the differences were between our search for planets in Kepler data using neural networks and other previous searches for planets in Kepler data using neural networks. Is that right?
Yes.
So one of the things that's interesting is that there haven't been very many searches for planets in Kepler data using neural networks. There have been a couple papers recently, maybe 2 or 3 papers recently, that have used neural networks to identify planets in simulated Kepler data, or which have shown that neural networks can identify previously known planets in Kepler data. But as far as we're aware, no one has conducted a search like this in Kepler data using neural networks. Does anyone else have anything to say about that?
This is Chris. Yeah, I think another part of the question, which I'll address, is about your question about the fact that we turned down the threshold of the search for candidate signals, and therefore we looked at the weaker signals. So just to clarify what we meant there, previous searches of the Kepler data would output the strongest signals, which are the most likely to be real planets, and then humans or other automated software would examine those to look to decide if they were new planets, if they were actual planets or not. In our search, we ran a similar search for signals, for candidate signals, and yes, we actually focused on the weaker signals, and then what we did was we actually applied our neural network model to those weaker signals to basically ask it which of these weak signals are the most likely to be planets. So that's the key difference with this work.
Thanks. And Chris, are there any other people at Google that are doing astronomy projects like this?
There's actually a large number of other science efforts at Google to use machine learning in science. I'm not specifically aware of any other Google efforts in astronomy specifically, but I am aware of other efforts to use neural networks, for example, to predict the properties of molecules, to detect diabetic eye disease, but I'm not specifically aware of any other astronomy projects at Google. But it's a large place, and so there very may well be some.
Thank you.
Thanks. Next we have Cesar Baima from Global Newspaper Brazil.
Hello, thank you for taking my question. I would like to know first if this kind of machine learning and artificial intelligence will or could be used on test data for the search of Earth-like planets, and how it would bring us closer to find a true Earth twin that is on the orbit of a sun-like star and on the habitable zone.
This is Chris. So I might take a stab at the first part of this question, where you asked about whether this type of machine learning will be able to be applied to the TESS mission.
Yeah.
So so one thing you'll recall about this work is that sort of the key ingredient was these 15,000 signals that had already been examined and labeled by human scientists. And so when the TESS mission launches, we won't actually have a set of previously known and identified signals. So there are two ways, I think, in which we will be able to apply this same sort of technique to the TESS mission. One approach is perhaps we could just wait a little while until some humans have actually labeled enough test signals in order for us to train a machine learning model based on the human classifications. But another perhaps more exciting area of research, but a bit more exploratory, is whether we can perhaps simulate some signals, for example, from the test mission, and then use those simulated signals to train the machine learning model, and then apply that machine learning model to the real signals. But that's a little bit more exploratory, and it may be a bit difficult to get that to work.
So this is Andrew. Your second half of your question was asking if this will help us find Earth-sized planets in Earth-like orbits around sun-like stars. Is that right?
Yeah.
Yeah, so I think that's plausible. So one of the reasons that these Earth-like planets around sun-like stars in these long-period orbits are rare is that they're just really hard to find. They're right at the edge of what Kepler can actually detect. So we're hoping that if we use this kind of strategy, of looking for the weaker signals and using machine learning to separate out the false positives from the real planets. We can boost Kepler sensitivity just a little bit more and hopefully be able to start finding these extremely interesting and exciting planets.
Okay, thank you.
And with that, we've got time for 3 more questions. We're going to take questions from the Business Insider, Popular Science Magazine, and then the New York Times. Let's go ahead with Dave Mosher from Business Insider.
Thank you for taking another question. I want to try to cram in just a couple more here. So, is there a catchy name or a simple name for this machine learning model other than that? You know, do you guys have a nickname for it? Should we call it the cats and dogs model? That's question number 1. And then I guess the other question is, help me understand, you know, there's a lot of other Kepler data, K2 data that remains. How many more targets are you going to look at, and how many planets do you expect to find based on what you've found in this initial run? And then if I have time for a third, I'll do that.
Hi, this is Chris. So for the first part of your question, no, we actually don't have a catchy name. So perhaps that's it's up to someone to suggest a good one for us. In terms of targets to look at, we have concrete plans to look at the remainder of the data set from the main Kepler mission, which is at least 150,000 more stars. In terms of how many more planets we expect to find, I wouldn't really want to speculate there because I don't know. One of the things which we did in this project was we searched for new planets around stars which are already known to host transiting planets, and therefore we know that the star already hosts planets where the orbits are aligned in such a way that the Kepler telescope can detect them. So when we turn our machine learning model to new stars, which may in fact have planets, there's probably going to be a lot of those whose orbits are not inclined such that the Kepler telescope can detect those. So I'm not sure exactly how many new planets we expect to find, but I certainly hope to find some more. And perhaps I can let Andrew add anything else.
Yeah. So it's hard to guess how many new planets we'll find, partially because if we find them, they're going to be in a new regime. They're going to be the smallest planets, and they're going to be the longest period planets. And if you go into a new regime, it's always dangerous to predict how many planets you're going to find because you just don't know. You've never looked before. So that's why we're doing it. We want to find out.
Okay, let's go to Robert Berger from Popular Science Magazine.
Hi, everyone. I'll make this quick and easy for you. I think I already know the answer to this, but is this the first time, to your knowledge, that an artificial intelligence system like a neural network has successfully discovered exoplanets?
So this is Jessie. I'll start with this, and then Chris and Andrew can correct me if I'm incorrect. So machine learning and artificial intelligence is a pretty darn broad category, and certainly versions of machine learning have been used to help us assess whether or not a signal is due to an exoplanet before. What this is the first in is this is the first time that, as far as we've been able to figure out, that a neural network has been used to successfully identify a planet. And neural networks are just really powerful algorithms, and it's really exciting to see it applied to this data set.
Yes, this is Chris. I believe, yes, I also believe, as Jessie said, that this is the first time that a neural network specifically has been used to identify a new exoplanet. And the other sort of first about this is that I believe we're the first to actually take a neural network and use it to explore this sort of new regime of data, this sort of weaker these weaker signals, and this presents a really great opportunity because there's going to be lots more weaker signals for us to look at when we actually turn to the full Kepler data set.
This is Andrew. Yeah, I agree with pretty much everything that's been said. I do want to call out, though, the discovery of LHS 1140b, which was discovered by Jason Dittman using the MERTH telescope. He was assisted by a neural network which identified which transits detected from the ground may or may not have been contaminated by bad weather and were false positives. So it's a complementary type of approach which has been used to help discover planets, but it's fundamentally a little bit different than what we're doing here.
Thanks so much.
Okay, last questions. We have Nicholas from the New York Times.
Thank you so much. The last question just sparked a quick question in my head, but I have two here. First one being, can you just give us one more time a simple layman's definition of what you mean when you say neural network? That's one. And then two, when we're talking about Kepler 90 and how it's 8 planets are all kind of scrunched together and how this is much different from our solar system, is it so much that the planets in that solar system are scrunched together, or is it that our technology can only see the planets that are really close to their sun that are scrunched together? So it might not be that out of the ordinary. Thank you.
Hi, this is Chris. So I'll take the first part of that question, and I'll try and describe a neural network in as few sentences as possible. So the way I would say a neural network is a machine learning algorithm that is very loosely inspired by the human brain, and it has a variety of uses, but let's focus on the fact that it can be used to classify inputs. So in this case, so we already talked about the question of classifying images of cats and dogs, or images of trucks and cars, or anything like that, or in this case, classifying signals from the Kepler telescope as being planets or not planets. So it's a type of algorithm that can actually classify inputs, and how it does that is it actually learns by example. So we're actually going to train this model by giving it a large set of labeled examples and allowing the neural network to actually learn which patterns in the input will it use to make the decision to classify the input as one category or another.
This is Andrew. I'll jump in for the second part of that question, which was about whether Kepler 90 is really that unusual, or is it just this is what we're able to see? And I think that's a really great question. When I think about what we know, it's very little. We have really complete understanding of just one planetary system, and that's our own solar system. And when we start asking questions like, what are the how does the solar system stack up to other planetary systems, we have to remember that we only have incomplete views. So we've searched for planets with transits a lot. That's how Kepler searches for planets. And as you said, transits are really mostly sensitive to close-in planets. We can search for planets by gravitational microlensing. Microlensing is sensitive to planets further away from their stars. Eventually, we'll be able to search for small planets using direct imaging, directly taking pictures of planets by separating the light from the planets from the lights of their stars. And all of these techniques will give us different views of planetary systems. And I think only when we combine those techniques together, we can get full views of exoplanet systems and start to put our own solar system into context and ask how common are 8-planet systems like our solar system with orbital spacings this far apart typically compared to the tightly packed systems like Kepler 90, or some of the really, really distant systems like the directly imaged planets around HR 8799.
Mm-hmm. So we just don't know yet.
Yeah, I would say that it's too early to say, and that's one of the most exciting things that will come out of the next few decades is we will get the technology and the missions to start looking for planets in these additional ways.
Mm-hmm. Great. Thank you.
And that's what we have for today's News Telecon. I'd like to thank the panelists and our operator for their time today. I'd like to ask the panelists to stay on the line for a few minutes for a post follow-up. If you joined this telecon late, you can listen to it again with the information that is on our press briefing site. To find out more about these findings or for more information on any of NASA's many programs and projects, visit us at the web at www.nasa.gov or via our many social media venues such as Facebook, Google+, Twitter, and YouTube. Again, we are holding a Reddit AMA Ask Me Anything on today's announcement at 3 p.m. Eastern, so please go to the subreddit Science for more information. Thanks for joining us and have a great day.
At this time, that will conclude today's conference. You may disconnect, and thank you for your attendance.
Guys, the holiday challenge is on at JCPenney. Shop now and get her all the gifts she'll love, like select fine jewelry for up to 60% off, plus an extra 25% off with your JCPenney credit card and coupon. And get $10 off when you spend $25 or more with coupon on select items throughout the store and at jcp.com. Get everything on her list for less than you think. Hurry in now, JCPenney. Coupon valid 12/14 to 12/16. Offers represent savings on regular or original prices. Credit offer subject to credit approval. Other exclusions may apply. See store or jcp.com for details.
break it off, you'll see who had it all. You had it all. You said you wanted to fall into oblivion, forget about the world we're living in. Fall into oblivion, 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 oblivion. Oh, going into oblivion. I'm going in. You can't fall asleep when you're counting stars. Get it together. Your mind can't sleep when you let it serve. And now you wanna see me fall. From a quarter mile, I can see you at the call. Think about it, ring won't tell you what I saw. When you break it off, you'll see who had it all. You had it all. You said you wanted to fall into oblivion, forget about the world we're living in. Fall into oblivion, 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 oblivion. Oh, going in. Fall into oblivion. I'm going in.
Like a broken soul in a wide like a broken soul in a wonderland without angels. This is how I feel when the mirror shows me a stranger. Yeah. And I know they're just fragments of a world where your absence all I get to see. Take me back to the planet where you and I are still meant to be.
Guys, the holiday challenge is on at JCPenney. Shop now and get her all the gifts she'll love, like select fine jewelry for up to 60% off, plus an extra 25% off with your JCPenney credit card and coupon. And get $10 off when you spend $25 or more with coupon on select items throughout the store and at jcp.com. Get everything on her list for less than you think. Hurry in now, JCPenney. Coupon valid 12/14 to 12/16. Offers represent savings on regular or original prices. Credit offer subject to credit approval. Other exclusions may apply. See store or jcp.com for details.